Greetings, 216ers. This is Professor Kaufman, and what follows is an overview of our last project for the semester. It will comprise two separate problems. They are distinct and not interrelated, so you could ostensibly take them in either order. However, they both retain or pertain to material that we've discovered recently in the course and will allow you to practice just a little bit with virtual memory and with spinning up threads to get some more performance in your programs. So the first problem is going to have you implement your very own version of malloc, a heap implementation that's not particularly complex, but is intricate enough that you'll get an idea of what might actually go on, and it's reflective of some of the actual implementations that are out there. It's referred to affectionately as malloc because there's an explicit list, the EL portion of that, and we'll get to that in a second. And then the second problem is going to have you do just a little bit of a matrix computation by doing some normalization of columns, and you'll get a chance to practice rearranging memory visitation order in order to improve performance, as well as spinning up threads to eke out yet more performance on those things. The code pack, the manifest for that is listed over here, and it includes some files for the first problem and some files for the second problem. Unlike in previous projects, there's pretty much, this will compile out of the gate. We'll see that in a second as we get started on this stuff. And so when you download the code pack, you won't need to complete or create, so you won't need to create anything. Rather, you need to complete this outline of the lmalloc implementation and then edit this call norm optim. It's a single function that's designed for you to make it run faster over a baseline version. Let's take both those things in turn. And so starting with problem one, this is generally referred to as a memory allocator. That's what malloc and its ilk do. And every programming language will have one, whether it's explicit memory allocation, as is the case in C, or a more implicit allocation scheme with a garbage collector, as shows up in Java and OCaml and virtually everything else, or wonky sort of in-betweens like that, which is used in Rust. Anyway, all of them have to interact with the operating system in order to get memory in the first place, and then partition it off according to some scheme there. Now, the pattern that we will follow is relatively simple, and I think it's best reflected using some pictures we have down here. Oop, I see. Let me pause this quick because I'm missing a few images here. Those are old, so they didn't get uploaded properly. Hang on just a sec. There we are. Picture is restored. I've reused these every semester, so they sometimes don't get uploaded properly at first. What I want to turn your attention to is a picture in the middle here, where this is essentially the heap. It's a contiguous big block of memory that will obtain through the use of some page allocations, that memory map function that we talked about. And it starts at some low address and goes to some high address. And this picture illustrates that globally, the heap is partitioned off into little chunks that will be referred to as blocks. Some of those blocks are in use, as in perhaps a stack pointer, some other part of the user program. It's pointing. Those in there are marked over here in gray. Versus others of those blocks are marked in gold. They are golden empty space that could be partitioned out and given as the result of a malloc here. That would change its color from gold to gray, indicating that's now in use. And that color coding is down over here. In between, keeping track of each of those blocks, are little headers and footers, the headers in blue and the footers in green. Each of the blocks, irrespective of their in use or available for use, they are going to have a header and a footer associated with them, and that allows them to be manipulated and change teams, if you will, be searched and so forth. And then overlaid on this will be a linked list of sorts. This is essentially what happens when an lmalloc call is made. I say, find me a memory block that's of a certain size. This in global memory will be stored the beginnings of that list, a little control data structure that says, go to the first available block and check, is it big enough? You can see it's got an A here indicating it's available. And if I chase this link, I get to another A block over here. That's also available. And then if I chase that again, I get to another available block over here. And then in each head, as well as each foot over here, is stored the size of those blocks. So this first available block is 22 bytes big. This next available block is 16 bytes big. And this final available block over here is 100 bytes big. Versus the in-use blocks that are tracked in this separate used list that are in gray, measure 256 and 38 and 20 and 60 bytes and so forth there. So if someone made a malloc request, please malloc 50 bytes for me, a typical approach would be, okay, we'll start looking at the blocks that are available here. This block is available, but it's only 22 bytes big, so we chase this link to find the next available block. Notice that that's not immediately sequential in memory. As in it's higher up in memory in this case. It might actually be lower down in memory because there's no reason these links need to point sort of sequentially up for convenience of diagramming here, but they do. But I'm not going to bother to look at this gray block in the middle because it's already in use. I should not grant it to a malloc call that would reuse the same pointer to data that and potentially provide the data that's already there and being used by the user for reuse, and that would obviously corrupt it. So we'll skip by that one by chasing this linked, and that will literally be a linked list sort of on a pointer there. And that allows me to inspect this one. I'm looking for a block that's 50 bytes big. The 16 over here says no, so it chases the finding one. And this one is definitely at least 50 bytes big. It's 100 bytes big. So the space in between here, this little yellow chunk is 50 bytes big. I could directly grant this as here's a block of 100 bytes big. It's certainly big enough to fulfill your request for 50 bytes. But a more common strategy is to split this up, to say, oh, split this in half and put a little foot and head over here. Talk about that more of that in a minute. And leave the 50 bytes of space here and whatever remains like in a tiny little yellow chunk over here. And then do a little bit of risk rearrangement because this will change this first part from yellow to gray because it's now in use, and we'll return a pointer to it up there. And that also means there are fewer nodes in the available list over here. So when things start out, this entire thing is just one big giant yellow hunk. That's your heap is completely available with a foot or a head at the beginning and a foot at the end. And it generally gets split up over the course of mallocs. As things are freed, they can be merged with adjacent yellow ones to sort of buff things up there. More to say about it in a second. So globally speaking, this is how the heap looks after some time. This wouldn't be right at the beginning of the program execution. Rather, it's some time after some things have happened, and perhaps someone wants some more memory or is freeing it, and so forth. But this is sort of an intermediate state where some blocks have been allocated, as others have been freed, and so on and so forth. So a few details. If you were to zoom in on one of these blocks over here, there's some pictures of that look like this over here. Here's an individual one that happens to be in use, colored gray here. The user, who is made a request at some point for please malloc me some bytes there, you'll return a pointer, and it's to this little payload, that this section in the middle over here that's of an arbitrary size. Has to be 16 bytes big, and if you had a pointer to this blue head here, you know that because one of the fields associated with heads is how big is it, what state is it in, and then pointers to next and previous nodes in this used list here. And the footer has very limited, it only contains the size associated with those blocks. So it's at the end here and says, likewise, it's 16 blocks. We'll get to why you need both a head and a foot over here in just a second. But the data types associated with this are shown over here. They're part of the malloc header, and you can see, each head has a size, a character indicates the state, and a couple pointers over there. Now, at various times, you'll need to traverse the heap in a couple different ways. One might be to say, hey, I've got a pointer here to this block that's this available block, and I need to find the next available block because perhaps I'm looking for something that's at least 40 bytes big, and this one's only 16 bytes big, so I need to skip it. So for that, you can chase this next pointer over here and go to some other place in the heap that has another available block, and anything that you'd find by chasing these previous and next links in here, this doubling linked list, will take you to other yellow available blocks and bypass all of the gray ones. That's one way to traverse the heap, is to visit all available blocks, or likewise visit all used blocks, as this gray used one over here. It has similarly some previous and next links. They bypass this yellow one and instead go to other gray nodes that contain blocks that are used right now. Another way that is important to traverse the heap is just to go structurally upwards or downwards. So you might be looking at this available block right here and say, I'd like to see what's immediately above it in memory, not by chasing any linked list nodes, but rather by doing just a little bit of pointer arithmetic. Now, looking here at this head, you'd know if I went the size of a head, which is this size was this size was the size of these two things forwards, this would get you to the payload that's in the middle of it. And that payload size is stored as a variable here. So you could add the size of a head plus this 16 here, and just doing raw pointer arithmetic, adding that many bytes, that would get you the foot. And then going the size of a foot forwards, that would as well get you to the next head here, the next adjacent block that's immediately above this one. Likewise, if you had a pointer to this block right here, the one that's sort of 8, that would point at here at this head that's in the middle here, you could go down the size of a foot, and that would get you this footer here. And then if you took that and said, let me subtract the 16 bytes here, that would get you past the payload and to the end of the head here. And if you subtract off the size of a head, that would get you to the beginning of the adjacent block below here. And so this adjacency business is something that'll be important, referred to by a couple of ways, like sort of structural traversal of the heap, or the next block up versus the next block in the list, things along those lines. Just bear in mind that this is done usually using pointer arithmetic, because you'd have a pointer perhaps to this head, and you could traverse upwards to the next head that's available by adding on the size of a head, the contents here of the size, so that's the size of this variable length payload here, and then the size of a foot together, and that would get you up, and likewise go downwards by subtracting off similar things. And this essentially explains why every one of these blocks also needs a foot. Imagine if this green thing wasn't here, well, I'd go down and be immediately in the payload, and there's nothing that says how big that is. And since these are arbitrary bytes, there'd be no way to find the foot below, so we'll use up just a little bit more space and say here, this will put an additional number here, a replica of the size, and maintain that, which allows traversal either forwards or reverse in the heap. So you have to maintain both of those. So 2 ways to traverse the heap: through the linked list nodes here, which stay in either available or used nodes, or just structurally by going up a block, up a block, up a block. The patterns that you'd see by traversing structurally in that way will alternate between used and available blocks. And this is sometimes referred to as fragmentation. It's like, oh, here's a little chunk, but it can't get any bigger because there's an immediately used block next to it. You may in some cases go used block, because someone mallocked and hasn't freed either of these over here. However, one of the things that we'll want to maintain is that you'll never go available block. There'll never be 2 yellows together. Because whenever a yellow block is freed, then we'll look around and see, can I merge it with other ones to make a slightly bigger one to reduce the amount of heap fragmentation that goes on. So that should make it sort of apparent as like, oh, if I wanted to make use of a block that's like 30 bytes big, there are 30 bytes here between this yellow block and this block, but they're separated, so they're not contiguous. And so neither of these could be used to satisfy a request, please malloc me 30 bytes. There's not enough space contiguous in these, even though they're together. I'd have to go to this next block over here and allocate it. And generally, there's not much you can do about that except try to limit it where possible. Rearrangements of the heap in C are just, they tend not to work out at all. And so perhaps with a little bit of effort, you might sort of futz around with stuff there, but generally you just sort of tolerate that kind of thing and leave it to the programmer who's, by virtue of using C, expressly said they want to manage memory fairly manually at this point. Okay, so let's talk a little bit of business about how this sort of allocation business starts at the beginning. So as you would find, here's a block that is big enough to satisfy some request. In this case, it's a request for 100 bytes. One of the steps that will be involved to say, oh, I have traversed along and haven't found any yellow blocks yet, but aha, here's one that I want 60 bytes in it. In order for it to be split, that means I need to have at least 100 bytes, because that's the size of a foot and a head combined, 40 bytes of overhead there. So on finding this block, you say, oh, this one is big enough. It's at least 60 bytes big. And as well, it's bigger than 100 bytes. That's the 60 plus the overhead of 40. That means I can actually break it into 2. So in the middle right here, through a little bit of pointer arithmetic, we'll plop down a fresh foot and a fresh head. Now, the semantics of the splitting business just say like, oh, create this new thing over here and return this second block that's been allocated here. We haven't decided whether it's going to go into used or available yet. This one doesn't change in membership, so that's an important part of the split is just, peel this thing off. But you can at least mechanically then plop this foot down here and this head down here. Students at this stage should recognize that if this is just bytes, of data that's in here, there's no type associated with it. And here's like where the power and mystery of C comes in, is like, just say, oh, at this position, I declare that I will treat this data as though it were a foot. And then 8 bytes up from that, I'll declare that at this spot, I'll assume that that's a head and put some data in there, like the fact that it's 60 bytes big. And then maybe jump up to this foot over here and change its size over here. Now, what was there is like just sort of arbitrary bytes, and truthfully, there's still just arbitrary bytes there. But since we're treating it as feet and head, this turns out to be like, oh, it more or less looks like a head and a foot then. So then this 60 bytes here can be partitioned off and used as a separate block to grant the malloc. And this other thing is what remains of heap space that can be granted in further mallocs. Now, there's a contrasting point to this split business is that, oh, I could be asking for 60 bytes, and this is definitely big enough for 60 bytes. But since it's not big enough to split, because it is not at the minimum of 100 bytes, it doesn't have enough to lay down another foot and head over here, then we'll just return this as like, nope, I'm not going to bother to split. I'll return null in a split like this. So with that operation at hand, it's possible to implement the lmalloc operation, which goes something like this. At the beginning of this, you would search through the heap and ultimately find this is the first block that I found in the available list that has enough bytes to allocate 60 from. Since it's big enough to split, I'll establish a separate head over here for what remains, and then resize this thing, so to shrink it down to be 60 bytes big. Notice that this thing still reads as available, and this one's in purple. It's like indeterminate what it's supposed to be. But after splitting off in this way, the lmalloc routine will say, oh, I have a block to do, cool. Let me make that available, because it is, and plop it down in the available list, and then take what was originally here, this head that was in the available list, it's out, and then I'm going to shuffle it into the used list here. And at that stage, I can return a pointer to just above the head over here, and that is exactly then where the user can point to put data in this spot. So I encourage everyone, study these pictures, because if you get the flow of the picture right, then you can start to fill in some of the code details of how this would look. To do this lmalloc routine, you'll first need a few other things, like the ability to split off a block, and that's also contingent upon knowing where blocks are above and below and doing a little point arithmetic, things along those lines. So that's the essence then of how malloc actually works. In fact, in the C library that we use most often, the glibc, the GNU version of it, that by default GCC uses. Now, the counterpart to that is to free a block. And so here's a case of a free where, hey, someone wants to free this thing, so they'll pass in a pointer. You just a little point arithmetic and say the block associated with the 60 bytes here is just beneath it, subtract off like 32 bytes or something like that. And so here is the block associated with it. An easy way to do that is just say, oh, you're going to change membership. Right now, you're in the used list. And since someone has freed you, you're now in the available list. And so insert this thing at the beginning of the available list. It'll have this little beg beginning pointer here that goes out the front. And then whatever was in the front at the end becomes after this thing. It's now out of the used list and in the available list. So this could be used to grant I'm allocated. Now, part of the reason that there's not much more to do here is because immediately to the left below this in sort of linear address space and above this in linear address space, these two blocks are still in use. And so not much can be done here. However, there do arise several other situations. For instance, if this was the block to be freed again, but the block beneath it happened to be free as well, then you'd convert this one to be excuse me, yellow. I'd say it's available, but then realize, oh, I've got two yellows in a row. This head in the middle and foot is just wasting space. Why don't I merge this entire thing? And so by jumping down one and saying also available, you can merge those two to say, get rid of this thing and just make this thing. It was 60 bytes plus 90 bytes. That's 150 bytes, but the size of this thing together is 40 bytes. So now I've got one big block that's 190 bytes big. And the pointer over here to the middle of this thing is no longer valid, but it doesn't need to be because this thing was freed. And at this stage is now a large block that could be used to grant further mocks. Now you can imagine, oh, if you just change the block here from 60 bytes used to 60 bytes available, and someone asked, please malloc me 100 bytes later, you'd find 90 bytes not big enough for 100, 60 bytes not big enough for 100, so you'd have to move ahead. But by virtue of coalescing these, merging them together in that way, then you get, oh, now I can easily grant 100 bytes because I've got 190 spare. Can even split that one up to sort of have a little bit left over on that. And so this is why the merging is done to try to limit the amount of fragmentation that happens. It can't always be done. And in looking at these cases, like here's a case where it can't be done, here's a case where it can be merged with the below, and as well, you'd want to check for alternative cases like, oh, can't merge with the below, but can with above, or I get here I'm freeing this, and there's a yellow over here, so I could merge all of these together. And so your code will need to attend to that part as well. So that's the essence of freeing. And will require the use of looking at the above and below blocks. Those are early functions that you'll write. And then tying a lot of that together, the merging with the free function. So finally, if it comes to pass that someone wants in this big heap picture, I would like to allocate 150 bytes. You could search the list and say, can't do that with here because it's 22, 150 is bigger than 16. Chase this, the last available us. 100 is not big enough to be 150. There are no available blocks that can grant this. And so there are two general approaches. The first is you just say, no, I can't allocate, there's not enough space. But most heap implementations will at least try first to say, can I grow the heap some ways? Grow it towards the stack, for instance. If there is more memory to be had, then I could potentially expand this to create some fresh and new blocks that would allow for this malloc to actually be granted. And so this is the subject of the heap expansion part down here, which is the section expanding the heap. This will attempt to append some pages to the end of the heap. The heap starts at a specific address and it goes for some number of pages according to the virtual memory system. And so you can use the mmap system call to say, hey, go to this address and tack some more on over there. Mmap then can be given a specific address. It could be the end where the heap ends. And so if you tack some more pages on, this will then, if it's successful, say, oh, here's some more space from the heap. You say, great, that's awesome. Let me just establish some blocks there, potentially merge them with the ending available block. But now I have a whole gaggle more space associated with this that it could be used to grant a larger malloc at that point that failed initially. Just bear in mind that the mmap usage there, that you can make a specific request, but the mmap system might actually return a different address or outright failure, and neither of those will be any good in terms of expanding the heap there. But this will grow the heap using the virtual memory system that we've talked about. Okay, so there's an outline for the code here that's provided in the project specification, but this outline is actually part of what's in the code pack already, and so we'll compile out of the gate. Let's just demonstrate that quick. I'm going to make a copy here of the link to the code pack and zip over here. I'll do the usual wget to download the code pack and unzip p5 code.zip. Should make it available here. Good. Okay, and if I change to a shell in there and just do a make, then you'll see everything compiles out of the gates. That includes several of the problems, the codes for problem 2, which we'll get to in just a second, but also the lmalloc stuff here. You're going to be doing most of your business in this lmalloc.c, and it's largely outlined appropriately already. You can see a bunch of functions provided in here that are part of it. And if we zip around a little bit ways, you'll eventually find some functions that are marked as required. And these are the ones that need to have definitions filled in for them. For instance, there's a function here that will grab linearly what's the next block that's above this one. And you see it uses this handy macro pointer plus bytes here that does pointer arithmetic in a sort of type neutral fashion. You're most encouraged to use that. Will work for, I think there's a pointer plus bytes and a pointer minus bytes described in the header file for allomalloc, pointer plus bytes and pointer minus bytes. So both of those are potentially useful. So you need to write the counterpart, the L block below, to take a pointer to something and go a little bit lower than that. Bearing in mind that the heap has limits as well, so don't go beneath the heap and return nulls in such cases like that. As well, there's a required function up here to say if I have a footer, find the associated header. If I have if I have a head, find the foot. If I have a foot, find the head. Things along those lines. There's basic sort of routines to navigate the heap in a linear way there. And then you'd move on to start working on required functions at a little bit lower down, such as the searching the list for available, adding, removing things to the linked lists that are associated with those. And so you have to look a little bit at the structs there. And then getting into allomalloc, merging, freeing, and the heap expansion over here. So it's like maybe 100 lines of code or so to finish this out. And it'll be good practice with pointer arithmetic and the assertion that we've made right from the beginning of the course that the bytes themselves have no meaning. So we can just overlay a data structure here and say, pretend this is a node, and voila, it becomes a node for the intents and purposes of the execution of the program. Cool. Okay, let's move on to the second problem, which is a numerically oriented problem. It asks you to do a bit of an optimization for a common operation that's needed in data mining, which is to normalize column data. And so oftentimes you get some kind of data in a big 2D table, a matrix here, where each row here is a measurement about something. It could be, this is how tall a person, well, let's see, tall is, okay. Tallness is maybe not the best way I think here. I'm trying to think of like things that have negative values. Let's see. Okay, so we'll just say this is like their latitude, the latitude of this person and the longitude of this person. They're negative. And then something about the average number of meals they eat per day. I'm struggling with the negative part, but these like different properties of person. They have positive and negative values. Like I'm not going to be able to come up with a good example here. And then here's a second person with somewhat different measurements about them, a third person with different measurements and so forth. And we're going to do some regression or modeling and want these to be more digestible by whatever machine learning model or statistical routine that we're going to use. And so it'd be very nice if this column were normalized. By that, I mean it will have an average of 0 and a standard deviation of 1. That's one form of common normalization for it. Now, since this would be like, height and weight and number of calories consumed and so forth, these each have very different sort of unit ranges. Some may be only positive, others in the thousands, others in just the fractional values and so forth. But lots of statistical methods then are less stable or become more stable if like, nope, everything has a mean of 0 and a standard deviation of 1, like all the numerical routines do a lot better in settings like that. And so the fine art here is to say, let me add up all these numbers, -6 plus -5 plus 7 plus 3 plus -4, and then divide by however many there were. There were 1, 2, 3, 4, 5 in this case. All of you should have figured out that's how you compute a mean, an average at some stage. And so that would be like, okay, I add up all those things, divide by 5, and my average is 1. We have to do that. Here's -11 and then 7, so that's -4. And then -1, and then -4 is -5 total. So my total here is -5. If I divide by the number of rows, that's -5 divided by 5, so it's -1 over there. Now, maybe less common to folks is to compute a standard deviation. Hopefully, most of you have done that because you've taken some sort of statistics class, college or high school or otherwise, Once you have an average, like -1 here, the process to compute a standard deviation is to go back through each of these numbers and to compute what's -6 minus a -1. So I would add 1 on and get a 5. Square that difference and add it on to some total. So here I've got a sum of 0, and I've computed my mean earlier on, that average up here. And then, I should probably fix that. It's not average, it's like mean, I called here, but it's the average right there. So square that difference and add it to the sum, and then go to the next value. So that would be the average is -1, subtract that off, so -5, so that would be 4. Square that, so that's 16, and add that on to this total that's over here. Do that for all of the values, and you get some very large sum. Divide that by 5 and take the square root of it, and that's what was referred to as a standard deviation. If you have a really small standard deviation, things are tightly clustered around the average, versus a wide standard deviation, a large, means there's a big spread around the average there. And hopefully you've all heard of the bell curve or the normal distribution. And essentially, you've got that hump, and if it's really tight and sort of steep, then that's a small standard deviation, versus if it's a really wide, flat bell curve, then that's a large standard deviation. And so the process of normalizing then, once you have these two things, average and standard deviation, is go back through this, subtract off the mean. So that'd be subtract -1, add 1 on here, and then divide by the standard deviation for this. Do that for this number, and then this number, and then this number, and then this number, and so on down the line. And that will get you a normalized column. So what was up here, -6, becomes -0.88. It's the approximate number of standard deviations away from the mean that this thing is. Different column is going to have a different average and a different standard deviation. Different column again, different average, different standard deviation for each of these. And so the normalization of the matrix then gives a transformed matrix over here. But if you were to go through that process again, find like, oh, the average in this case is 0 and the standard deviation is 1. And that means it's normalized. So the routine that you are all going to optimize is given down here. And it basically takes this dumb little algorithm over here, which is good for a single vector of data, this little array len over here, and does so for an entire matrix. And it does so in the naive ways, like, okay, here's my little matrix that's up here. And what I'm going to do is to march down, I'll fix a column. I will go on column 0. We'll go down that, I'll compute an average for that jth column, and then set the output vector here, this average business here. I'll set that to be the average that is computed, reset my sum to here, and then go through and do just as that upper loop did, is subtract off whatever the matrix element is from this average, and then square that and add it onto the sum. When I get done with that, I'll take a square root of that, or to divide by rows, and then take the square root, and then set that to be, and then visit all of the matrices, extra elements in the 0th column, subtract off the mean, divide by the standard deviation over here, and voila, I've got a normalized matrix along with the transforms, the average and standard deviation that was used for that. So essentially 3 answers: transform this matrix to a normalized version, and make sure that these 2 vectors here, they have the average and standard deviation for each of the columns that are in. So this is done in a sort of dumb way, as in go down each column, go do this for the 0th column, and then do this for the 1th column, and then do this for the 2th column, and so forth. And so involves quite a bit of, here's a tight loop that will say fix a column and then change a row. And most of you should realize at this stage, based on discussions we've had in lecture about caching and memory visitation order, that fixing a column and going to the next row is going to miss cache. And so this will have poor cache performance. It's an opportunity then to try to reform this in such a way that you get better cache performance. Figure out some way to go across a row and compute some things in that fashion. Might involve the introduction of some additional data up here to say I can't keep track of all this sum on its own now. I have to keep track of sort of some running sums or something like that. But the biggest optimization to do from the get-go is going to be to somehow invert these 2 loops, the I and j loops here, while still preserving the answer that's computed across the pair of nested loops here. As going across a row will improve the memory performance there. The next step along those lines is to figure out once you've transformed in that way, how do I utilize multiple threads to make this happen? And so let's see, there's some discussion somewhere around here, optimized column, that you will probably want to employ multiple threads using the pthreads library that we're going to talk about later today. There are a few constraints on this that I think are worth mentioning. For instance, you will obviously you're going to have some shared data across the threads, and so should find the occasion to use a mutex to coordinate access to that. Those are things that we'll be talking about during the course of this week. Our last topic is threads and coordinating access of shared data using mutex, common par for the course there. It's also something that's being discussed in the most recent lab 12, that's going, is the subject of conversation in the, the discussion sections this week. And so using 1 or 2 or 3 or 4 threads is likely to get you faster speed if you can coordinate their activities properly in order to split up the work of the matrix and then as well gather up the data that's required into a shared location in a coordinated fashion there. We'll look in just a second at the benchmark that's used for this. But what you'll want to do is to respect there'll be a parameter to a function that you have to write that says, here's how many threads you can use. And most folks will want to then fire up that number of threads. We can't check that but for sort of manual inspection, so be aware of that part there. And we'll probably run your code on 1, 2, 3, maybe 4, maybe 1, 2, 4 threads, something like that. So use as many as you can, and they'll be tied to the cores that are on the machine. You should try to avoid using global variables. It's tempting to use it in some cases, but here our emphasis is going to be upon making this a sort of library-like function so that you could have within the same application 3 or 4 threads call your multi-threaded version of this thing, which would spin up more threads there, and it would be safe for that. Global variables would negate that safeness, and we'll discuss more in detail about how that looks in a lecture example that's coming up relatively quickly. So there's a benchmark that's associated with this, and let me just turn your attention back up to this thing here. I just want to say here, we've retuned this so that it works on any Grace machine, but if you run it at home, it won't look quite right. You just run it by compile your code and then run call norm benchmark, and it will run on a series of sizes over here of matrices and pass in some number of threads to it. Now, there's a baseline version that's provided. That's the one that's actually, we just sort of talk through as sort of the dumb way that goes down columns out there. And your code will be measured based on its speed up over that baseline version. So over here is the time that it took the baseline version to run and the time that it took the optimized version to run. And you can see it's a tiny little speed up. It went about 1.16 times as fast. So this is 0.31 divided by 0.27. That's here, the speed up, that's that ratio. But as I went to more threads, I got almost a 2x, a 1.5x speed up here by using 4 threads. Not quite a 4x speed up. It's hard to do for small sizes here. Now that's used in a formula then to compute some number of points here, and the running total of points is listed over here. So got about a 1.72 points over here after this sort of smallest size matrix with 1,100 rows and 2,200 some columns. Next size up matrix here, the baseline took 0.2 seconds to run, but I was screaming along for my optimized version, 0.75, and even shorter than that, getting pretty much a 4x speed up here for the 4 threads that were used. And as the matrix gets larger, I'm getting better and better performance. You'd expect that because as the matrix size goes up, the cache problems for the baseline version get worse and worse. But if you've resolved those in your optimized version, then your version, even the single-threaded one, will scream along. You can see here's an 8x speed up even on a single-threaded version because I solved all the memory problems. 2.5 seconds, try 0.3 seconds over here. So a large lion's share of the points that you'll earn will come late in the benchmark as the matrix size is larger and more pressure is put on the program because it can't fit everything into cache. If the entire matrix fits in cache, then hey, life is good. Like it doesn't really matter what order you visit things in. But as soon as it gets too big to fit in the inner caches, then the memory ordering that you pick is going to have a huge impact here. We're talking like now 9x difference just on a single thread out there. And so focus your attention on not so much the smallest sizes, but making sure that visiting memory in the proper order will get you better performance in the larger sizes. If you greatly exceed the, well, here we've partially exceeded the 35 points since it's been truncated down, but if you greatly exceed this at a couple different levels, there's some makeup credit that's available for you. And I know I need to update the spec here. There's some warnings here about, oh, you're not running on the right machine here. This will actually run on any Grace machine as far as I know, although the operators for Grace keep screwing around with things. And so I need to get a hold of them and find out if they screwed this one up about right now. But for the plan right now is this should run properly on any of the Grace nodes without modification. Finally, then, in terms of debugging, multi-threaded stuff gets snarly really fast. And so you want to be very cautious for this. One possible way to help with debugging is there's a little printing routine that's provided, this call norm print.c. And here, this calls the baseline version and it also calls the optimized version and just prints out, here's what the answers should be here. And lets you sort of check to see, my answer, is it match the baseline version? Because these two are supposed to be computing the same thing. And if they don't, then something is off about it. Here's a case where something went wrong in terms of the version here that the optimize doesn't match at all what the baseline is. It got a bunch of nans in there. And this is the original matrix, but it's not been normalized properly according to this. And so just keep that in mind as a handy utility to use. Is you can pass in smallest size matrices. That's the first two parameters. And then how many threads do you want to use? Things tend to work reasonably well with one thread, but as soon as you introduce two, if you're not coordinating right, then this can go haywire. Just for reference, then, in the code pack itself, there is this series up here of call norm stuff. The benchmark is here. It's the program. You can have a look at it as you want. The header here includes the data types, and these are introduced both in the labs and in the homework, and also I think in a lecture we'll talk briefly about this over here. As this is a matrix, it's a little data structure. It's stored just as a big giant array, and you can use some macros to get individual elements from this matrix, the ijth elements, from this vector, the ith elements, or to set elements, to say set within this matrix the ij thing to be some other data over there. Good reference for that is the baseline, which is, let's see, call norm base dot here. It has usage of those macros over here, and they shouldn't be sort of hard for you to get used to. Incidentally, this is a good time to say this is what a macro is in C. It's like you pound to find something, and it means this little thing here, as it would show up in code, it will be replaced with this gobbledygook over there, which is just a short bit of arithmetics to compute what location in the matrix that thing is at. To that end, you can make use of macros if you want. You can also break those open, which there might be some savings there if you know what you're doing. But I'd encourage folks to use them to begin with first, and then only later as they're trying to eke out more and more speed, resort to breaking that out, because the code is just going to end up looking less readable without using them. And then the version that you'll have to write is in this call norm optim.c. Now over here, one of the required elements is you'll have to run your code on Grace and get whatever your best sort of foot forward is for benchmarks to copy and paste the results of that benchmark in your source code over here. This thing's set up so that there's sort of an entry point here, but then you can write several different versions as you evolve that. It's like, oh, this one is pretty fast, and make a copy of it and make some tweaks here and just call the B version over here instead. So you're good to go. This thing works out of the gate. You saw as I was compiling over here, like this thing compiled so I could run the call norm benchmark. It'll run on my laptop here. And so complain a little bit about this. And also, you have a whole litany of complaints here, and that's I'm computing incorrect answers. And so I'm not matching the baseline, and so I'm going to get 0 points from it. So this comes all the way down here with a big fat 0 out of 0. It's fine and dandy to go faster, but if you compute the wrong thing, as in this was supposed to be minus 0.23 and it was -2, then that's a fast wrong answer. So may as well just return a random number at that point. So make sure to check your answers there with a benchmark over and over, looking not just for speed but also for correctness, because your score drops to 0 if you get things wrong. which you expect like when we haven't written any code yet. The Opta version here just does nothing right now. All right, I think that's all I have to say about this. Just a few corrections to make here in order to straighten out that you can run on any Grace, no, not just the odd ones. And yeah, happy hacking to all. This will be our last project of the semester. Not terribly long for either of these, but very instructive of the things we've been talking about in lecture. So enjoy.